All right, so again, for those of you online, our lovely book has a table of contents, and in that table of contents, there is a review of precalculus, and that review of precalculus has some lovely identities. So we're going to use some of these basic identities here. The thing we use the most are the Pythagorean identities. Other identities, last class I said are going to be handy, are the double angle and half angle formulas will be helpful. And for one problem, the angle sum and angle difference formulas could be helpful. So mostly this section is about using trig identities. So problem I want to look at first is the integral of the sine of x times the cosine of x. Just note, for any one of these trig intervals, there's probably at least 2 different ways to do them. Okay. And a way might click based on a trig identity you remember, or maybe based on a problem you did recently. Anybody want to suggest an approach to this one based on last class?
Instead of the
Let u be sine, yeah. Or we could let u be cosine in this case, but I'm going to go for sine. So let's let u be the sine of x. Du would then be the cosine of x dx, which is lovely because I have u and du sitting there with no fiddling. So this becomes the integral of u du. Antiderivative for u? 1/2 u squared plus c, and then we put sine back in, so we get 1/2 sine of x squared. What am I doing there? You guys, you come to class?
Wait,
Okay. Plus c. All right, so I forgot to post this to Google Plus in case any of our high school friends want to join us. Actually, oh yeah, so they're just out of luck, yeah.
Yeah, so their schedule's all messed up.
Oh, well, you can put it up there just in case.
Really rough.
Okay, back to work. I'm going to suggest another way to do this. The blue function, my integrand, reminds me of a trig identity. Good question. I think it looks like the double angle for the sine. Anybody remember the sine double angle formula? I believe it says the sine of 2x equals the sine of x twice the sine of x times the cosine of x. I think.
Sine is 2 sine a cosine.
Yeah, that's it right there. Okay. So my integrand is just missing the 2. Right? So I could just say then that 1/2 sine of 2x is equal to the sine of x times the cosine of x. So now my integral of the sine of x, cosine of x, dx, could also be written as 1/2 the integral of the sine of 2x. Antiderivative for this guy?
You have a v substitution, right, for 2x?
Yeah.
Mm-hmm.
So it would be
So v equals 2x, dv equals
2dx.
2dx.
So then you get the 1/2 dv equals dx.
Yeah, so I'm missing that factor of 2, so that's going to throw in another half. So what's going to happen here is I have the half on the outside. That's going to give me another half. And then antiderivative for the sine is the
Negative cosine.
negative cosine, so I'm going to throw a negative in front. Cosine, and I'm going to put the 2x back in, plus c. So negative 1/4 the cosine of 2x plus some constant c. That's not the answer we got last time.
But wait.
The same thing.
That one says it's 1/2 the sine squared. Uh-oh, did I make a mistake?
I guess sine squared equals something.
You gotta use the identity.
Sine squared equals 1 minus.
Okay, here's the deal. This c right here ain't the same as the other c.
So there's multiple
That can get
equations.
So it turns out if I were to set those two equations equal to each other, I would find they're different by some constant, is what I'm going to find. Okay, so what's my point here? My point is there's more than one way to do any of these. Because of all the various trig identities out there, right? Sine and cosine are complicated little critters. That means there's going to be different looking answers, very different looking answers, that it's not obvious they're equivalent because of the plus c. Because they're different by constant. Okay? So you might do a homework problem and maybe you get it right and then you check their answer and their answer looks nothing like yours. That's okay. There's just different ways to do these. You just pick a different route in the scheme of trigonometry to go about it. All right? Just the way it is. Right? So if you're bored later, right, you could set that right there equal to this part right there and try and solve that as an identity. And what you find is they're not perfectly equal, they're just off by a little bit. Like maybe a +1 or -1/2 or something like that. And that's just because of this arbitrary constant deal with integration. Right? So these are fun and exciting, and we get to try and remember all the trig identities we tried to forget.
So they're not going to be a test.
What's that?
So they're not going to be a test. The trig identity. Like, we'll have GC for all trig identities.
I will give you every trig identity I think you need for the test.
Oh, okay.
Yeah. But sometimes it's nice, well, after this assignment, you're going to rememorize a whole bunch of them because you're going to keep looking at them. It's just going to happen naturally. How about, well, this was a cute one. The integral of the sine squared of x times the cosine squared of x. Now, with the first problem we did, it was nice to say, hey, let's let u be the sine, because then du would be the cosine. But the problem is I don't have a single cosine chilling out here. I have a cosine squared. Right, Kyler?
Is this the integration by parts? Is that what you're going over, or is it 3?
No, we're doing 3.2.
Okay.
Yeah.
Some identities trig again.
Yeah, so what we have to do is apply some trig identities because a regular substitution is not going to work on this one right here. So there's a couple of different identities. Yesterday, identities I went over were the half angle formulas. So that would be, for example, the sine squared of x is equal to 1 minus the cosine of 2x over 2, and that the cosine squared of x is equal to 1 plus the cosine of 2x over 2. And, yes, sir?
Another identity would be like, cosine squared x would be 1 minus sine squared x.
Also, we have the trigonometric identity, which is, the Pythagorean identity, cosine squared of x plus sine squared of x equals 1. So we could solve either one of those for the sine or the cosine. I'm going to throw one more at you.
What?
That the, we just figured this one out, that the sine of x times the cosine of x, right, the sine double angle formula, would be, usually there's a 2 on this side, I'm going to move it over to the other side because of the way that looks, is equal to 1/2 the sine of 2x.
And you can use all those?
You could use, well, you're not necessarily going to use all of them.
Well, I mean, you can use.
But you could use any one of these to attack this. Yeah. So anybody want to suggest a way to go?
I like the.
Last method.
The last one?
Yes.
Okay. What were you going to say, Carter?
I was going to say that cosine squared plus sine squared equals 1.
Okay, yeah, that's another good one too. All right, split up into groups. Everybody pick your favorite set of identities there and see what happens. I'll do it a couple of different ways just for fun. Rob?
Well, I was going to say, wouldn't you just use the cos squared would equal to 1 minus sine squared?
Yeah, you could replace the cosine squared with a 1 minus sine squared. Yeah. Yeah. There's lots of options. Just pick something and give it a shot. See what happens. I'll start roughing it out a few different ways. And remember, with the double angle formula, or the half angle formula for sine and cosine, the divide by 2, right? You could view it multiplied by 1/2. All right, so I'm going to start a version and then move to another one in a moment. So here I'm applying that first set of identities. What's the double angle say I should do there? So the formula says whatever variable you have here, double it over there. Yeah, so it's going to be 4x over here. But now, so the nice thing about the half angle formula is you can also think about it as a power reducing formula. Because I had a cosine squared, which was a problem. Now I just have a cosine to the first power. I got to trade it for 4x inside, but I reduced the power. That makes sense? Okay. So that one's totally doable now. If I try that second, and I'll come back to this to finish it in a moment. If I go to that second method where I try using the Pythagorean identity, then I would get the sine squared. Maybe I'll keep that one, and I'll trade the cosine squared for 1 minus sine squared. So then I have to distribute. So I'm going to get a sine squared of x minus a sine to the 4th of x dx. Now, when I have a power of a sine, I really like having a cosine next to it, but I just got rid of the cosines, so I might have made myself more trouble. We could reduce this by applying the half angle formula to it, which reduces the power. And then I would have to apply the half angle twice to that to reduce the power. So I think I actually made more trouble for myself with that. Okay. So I'm gonna abandon this one. It feels like I just made more work than the other way. So
I was gonna share what I
did you do the last way?
I did it probably a little different.
What's that?
I used 2 different identities,
Okay.
one after the other.
So what did you do?
I used the sine x cosine x equals 1/2 of sine.
Okay. So
I'd have to.
so then we have to view this as the sine of x times the cosine of x all squared.
Yeah.
Right. So then we can use the sine double angle formula So that's going to give us that right there inside the parentheses. The square is still outside, is 1/2 the sine of 2x, right? Okay. We have to square everything, so this becomes 1/4 the integral of the sine squared of 2x. Okay, then what did you do, Siler?
And then I use the double angle for the sine squared x.
Okay, so then we rewrite this one right here. So the 1/4 is chilling out front. The formula you're referring to is this one right here. Yeah, and again, whatever this is gets doubled when we use that formula. And so then we're going to get the integral of 1/2 parentheses 1 minus the cosine of double that angle, which would be 4x dx. And now I have it to a place where I can find each antiderivative. Okay, so let's do that and compare the two.
How'd you get cosine of 4x?
The formula, oops, too far. This one, yeah, says that if you have a sine squared of some angle, you can replace it with 1 minus the cosine of double that angle.
Oh.
Okay, so the angle is x, I have double whatever x was. So if I started with a 2x over here, it becomes a 4x over there. If I started with a 3x over here, what would it be on the other side?
6x.
It would be a 6x, yeah. And we're going to see that a few times in this homework. Yeah. Okay, so let's finish them up and compare what they give us. So let's see, I still need to finish this one here, and then I'll go back to the other one. So I think the last method, I think that was the easier one. But I don't know that till I've done them both, right? So you just got to try something. And if it looks like you're getting in over your head, say, maybe I need a different identity. So this one here, let's see, I'm going to get 1/4 x minus, I'm going to have a minus 1/4 times 1/2. Antiderivative of 1 is x. So minus 1/8 x. And then I'm going to have a minus 1/4 times 1/2. Antiderivative for cosine, sine. So I'm going to leave a little space. I'm going to write the sine of 4x. Now, if I had taken the derivative of the sine of 4x, what would happen to that 4? It would pop up front. It's not there, so I need to compensate with a 1/4. Okay? If that is messing with you, like Carter said earlier, do a U substitution, call that thing U, to help figure out the constants. And then we got a plus C going on with that. So let's see, a 4th minus an 1/8 is 1/8. And then over here, I'm going to have a 4th times 1/2 times a 4th, which is what, 32nds?
Yes.
Okay, so this version gives us, see if I can write this properly. So method 1, 1/8 x minus 1/32 times the sine of 4x plus some constant c. Maybe we'll call that one C1. The second method didn't seem to work out. I'm abandoning that one. The third method is going to be productive. Let's see, is that this one here? Yes. So let me shrink this and clean it up. All right, I just need one more line to finish it, I think. All right, so let's see. We are here. So 1/4 times 1/2 is 1/8. The antiderivative of 1 is x. Minus, I'm going to bring that 1/8 in, antiderivative of cosine.
Yeah, sine.
Sine, yeah. And then if I take the derivative of that, there should have been a 4 out front here. That 4 isn't there, so I have to compensate with a 1/4. This negative, I got it right here. And then a plus C. Hey, that's what we got the other way. So sometimes different identities work out to the same answer, sometimes they don't. There it is. And the identity you pick will depend on what you remember from yesterday, what you had for breakfast, how much sleep you had. I mean,
How can we know if we got it right?
take the derivative of that and see if it gives you this back. Now, if you take the derivative of that, might some identities be involved?
Yes.
So are we guaranteed to get exactly back to where we started? No, we'll get something equivalent. That's an identity.
Yeah.
Okay.
Let's check.
For you.
So we think 1/8 x minus 1/32 sine of x to the sine of 4x is the answer. Let's take its derivative and see what happens. So I think I had some room back here to do that. All right, so we're going to try and check by taking the derivative with respect to x of all of that. All right, derivative of 1/8 x. 1/8 minus the 1/32 is a constant, and then the derivative of the sine of 4x would be 4 times the cosine of 4x. And the derivative of c, goodbye, it's 0, right? All right, so this cleans up a little bit. 4/32 is really 1/8, which I can factor out. So now I have 1/8 times 1 minus the cosine of 4x.
But you can,
So that is supposed to be equal to the sine squared of x times the cosine squared of x. Okay. So we could apply some identities to that, or this, to try and get them to look alike. One sec, William. Or we could graph them and see if the graphs look the same. Yeah, William, what were we going to say?
Didn't you forget something cosine 4x, like outside of?
So I said it, but I didn't do it. So 1/32 times 4 is 1/8. And so I factored the 1/8 out front. And so that left me 1 minus the cosine of 4x. Sorry for skipping that step. Yeah, so if I graph these two, they should be the same graph. They should sit right on top of each other. Etor gives me a thumbs up on that. Yeah. So pre-graphing calculator days, I had to apply identities and hope I could find the right identity to get those two to match. Graphing calculator days, we can just graph two derivatives and see if they line up. And they should line up perfectly. So what's another way to check? Like if we look back at that first problem I did, one answer was -1/4 cosine of 2x, and the other answer was 1/2 sine squared of x. Keep in mind the plus c. If I were to graph these two antiderivatives, what do you think the graphs would look like with respect to each other?
just a little offset.
They would be parallel vertically to each other. Yeah, one would be vertically shifted up or down from the other one, is what I would see if I did that. But they would have the same shape otherwise. Okay. All right, what other funny games do we have? Carter had a question. I believe his question was about number 13 from the homework. So I'm going to look it up to see if that rings a bell. 13 in the homework says, from 0 to pi, integrate sine of 3x times the sine of 9x. Does that ring a bell?
Yes.
Okay.
Unfortunately.
All right, so this is an identity problem. All right, so we have identities that turn sums to products and products to sum. So what we need to do for this one is we need what's called the product to sum formula for sine and cosine. And so we'll just look that up. I could show you how to derive it. If you guys did that back in Trig, you don't need to do it again. That formula is not a common formula, so it's not going to be listed on our summary here, but you can derive it from this group of formulas right here, okay, if you were desperate. But we're not desperate because we have the internet, and you can find anything on the internet these days. I'm sure there's a YouTube video of a goat doing calculus somewhere. So let's see, I want Trig, I can spell identities. And let's see, I think we looked at math is fun yesterday. I'm sure Wikipedia has a great page. Let's try math is fun. And we are looking for product. Oops, Control F. There's a lot of trig identities, so sometimes I just search the page for the word I want. But not here. Really? They just give common ones. Okay, so that one didn't work. Wikipedia, purple math. Let's try purple math. I've been there a long time. Purple math trig identities. Control F. Product identities. Okay, so here they say, hey, if you have the sine of something times the sine of something else, it's 1/2 times the cosine of the difference of those two angles minus the cosine of the sum of those two angles. So that's the identity we want. I'm going to copy that into my screen. And again, you will have a set of identities for the test. All right, so let's see. So now we have the integral from 0 to pi of, let's pull the 1/2 out, cosine of 3x minus 9x is a negative 6x minus the cosine of their sum, which would be 12x. The antiderivatives. Now, with derivatives, I would be hoping to see a negative 6 multiplied outside here, for example, or a 12 multiplied outside there, but they're lacking. So I'm going to have to accommodate some fractions. 1/2 is chilling out front. This one's going to give me a negative 1/6 sine of negative 6x. The derivative of the sine is the cosine. The negative is there because of the negative 6. Minus a 1/12 times the sine of 12x. Those parentheses, and we want to evaluate that from 0 to pi. Let's see, sine of pi. Anybody remember? 0. Sine of pi, 2 pi, 0, 5 pi, 9 pi, 6 pi, 12 pi. Sine of anything pi, any whole number pi, any integer pi, sorry, is 0. So, what do I get here?
0.
Well, when I plug in pi, I get a 0 minus a 0. When I plug in 0, I get 0 minus 0. So the answer here must be
0.
Or maybe it's 1/2 times 0. Just kidding. All right. 5 is not 5. It's 0.
That's
So what must happen graphically? If you graph this function right here on the interval from 0 to pi, what you're going to find is exactly half of the area is up top and exactly half of the area is down below. Now, is it going to look like a perfect wave like that? No, it could be super wiggly, and it probably is super wiggly. Okay. but we'll have cancellation of positive area and negative area. If you look at that graph. So that means this function, half of it sits above the axis between 0 and pi over 2, the other half is below. And again, this is not an accurate rendering of that function. Yeah, I think this is going to be like an amplitude modulation kind of, I'm kind of curious what it looks like when I graph it. So we have the sine of 3x times the sine of 9x, x. Yeah, this is kind of a cute one. Is this amplitude modulation or frequency modulation? Let's see, which has the greater period? Let's graph the sine of 3x next to that. Yeah, that kind of works. And check out the negative sine of 3x. Oops, nothing there. Negative sine of 3x. So the green function is our function. The sine of 3x has the bigger period than the sine of 9x. So when you multiply two sines with different periods, what happens is that multiple oscillates inside the boundaries of the other one.
You got one oscillating, then you got.
So you get this big thing oscillating, and then the product oscillates inside of their as a wrapper. Yeah. So the sine of 3x acts as a wrapper for this product. And if you raise that 9 to something like 100, you just get more oscillations inside there. Isn't that cool? Yeah. This is how radio works. Yeah. And there's two ways to do it. There's to stuff one wave inside of another wave, or to let the other wave wiggle on top of. So you get a sine wave wiggling on top of another one. So there's amplitude modulation and frequency modulation. So this is this one is amplitude modulation. What's that?
So what would happen if you put the other sign next to 100x also instead of 3x?
Oh, then we would have to really zoom in to see what would be happening.
Would it just fill out even more?
If you made that a 200,
Or 100?
or if you make it 100 also, then I can't remember what will happen. Well, now the 3 is irrelevant because now these things are, it's only interesting if they have different periods. Yeah, and it's this. Yeah, so once I put them the same thing. If I make it a 200, it's going to look very messy because now they're oscillating within the sine of 100x, and I would have to really zoom in to see what's happening there because these things are oscillating so fast. So on this scale, I can't see what's happening. But if you zoom in, it'll look just like that first picture we saw. Okay, is what would happen.
So with the previous, the 3x and the 9x, would the 3x be what they call the carrier wave to the 9x wave?
The 3x would be the carrier waves, yeah. Or it's more like an envelope wave. A carrier wave is when you add one trig function to another, and then one function wiggles on top of the other function.
Yeah.
Not within, but on top of, or over, right? So let's see if I can easily show that here. Suppose we have the, let's delete some stuff. Sorry. Start over. No, delete. Okay. So suppose we had the sine, let's just use the sine of x as our carrier wave. And then what I want to do is I want to take that sine of x, take that sine of x, and add to it something smaller, like let's go with 1/10 times the sine of, let's go with 10x. So now this function wiggles on top of, so that's frequency modulation, where I have one wave ride another wave.
So the first one was AM radio, that's FM radio.
So this would be FM radio over here. Yeah, I should have picked a better color for that. So that's FM radio there. Yeah, pretty cool stuff. All right, we got time for one more maybe? All right, what, I know. Really want to do an application, but I don't have time. Let's take a look at number 4 or 5. There's so many cute problems to do. So most of the problems you're going to do are going to be applying the Pythagorean identity for sine, cosine, tangent, secant, cosecant, cotangent. All right, let's do number 5. 5 looks cute. All right, so I think I did a problem like this yesterday, and the nice thing about the problem yesterday is that the secant squared was hanging out, which is the derivative of the tangent. Now the problem here is I have odd powers, not even. And so there isn't a tangent squared hanging out, because if I pull off a tangent squared, I'm going to have a regular tangent floating around, which is going to be a nuisance. Instead, what I see here is if I pull out a secant times a tangent, so that means I'm going to write the secant to the 4th, so I'm going to reduce that by 1. I'm going to reduce the tangent by 1, and then I'm pulling off a multiple of secant times tangent.
So it's just factoring in the secant tangent right now.
And the secant tangent is the derivative of what function? Secant. Okay. So I'm thinking I want secant to be my u, because this would be my du. Problem is the tangent squared is sitting in the way. But there's a Pythagorean identity for tangent squared. So you remember what it's equal to? Almost, not 1 minus, but 1 plus secant squared. Yeah, so I'm going to double check that in our identity sheet in case my memory has failed me. Purple math, Pythagorean identities, right there. Nope, you were right, Rob. Tangent squared is secant squared minus 1. Okay. So we're just going to replace that tangent squared with a secant squared minus 1, which is going to mean we're going to have some distribution. So we're going to be neat. So the secant to the 4th is going to get multiplied by a secant squared minus 1. And I'm just going to leave that secant tangent hanging out on the end. I'm not going to touch it yet. I need to distribute the secant to the 4th through there. So now I'm going to have the integral of secant to the 6th of x minus secant to the 4th of x. Parentheses around that difference, because it's being multiplied by that secant tangent, dx. Now I can do a u substitution. What are we going to let u equal? And what is du going to be? Secant tangent dx. Okay. So I'm letting u equal the secant, and du happens to be sitting right there on the end. So this becomes the integral of u to the 6th minus u to the 4th, parentheses du. So the derivative of u to the 6th would be u to the 7th over 7. But what is u? Secant. Secant, yeah. So then putting that all together for my answer, I'm going to get the secant to the 7th power over 7 minus the secant to the 5th power over 5 plus c.
And it doesn't make a difference if you were to do 1/7 times the secant.
No, you can call it 1/7, yeah. All right, do we have time to set up one more? Oh yeah, we have 3 minutes. All right, the end of the assignment had some applications. One was area bounded by 2 graphs, another was arc length, and another was volume. Let's go with the area problem, number 15. Homework, new page. 15. All right, so my version has the sine of x, the sine to the 5th of x equals 0, and x equals 1/2. We're probably going to want a graphing calculator to get a picture of these. I do not know what the sine to the 5th looks like off the top of my head. It's a tough one. All right, so calculator time. So let's see. Again, sine and sine to the 5th. So half of x equals sine of x. G of x equals the sine of x raised to the 5th power. Ooh, that's a cute little wiggly thing. And we're interested in graphing from 0 to x equals pi over 2, which looks like their intersection. Yeah. All right, so the big thing we needed here was to identify which function's on top, which function appears to be the top function, the sine of x, and then the sine of the 5th is underneath that. All right, so back here, just determined by graphing that this is the upper function and this is the lower function. And in this interval, since they don't switch, that means we just need one integral. We don't have to break it into multiple integrals. And that's the main thing I needed to check. So then this is the integral from 0 to pi over 2 of the sine of x minus sine to the 5th of x. So the sine of x isn't a problem, but the sine of the 5th power is a problem. So I'm just going to attack that one separate. So just a quick setup on that. I'll explain what I would do. So I need an antiderivative for the sine to the 5th of x. What I would do with that right there is break off a sine. So that would be sine to the 4th power times the sine of x. And then guess what I would do next?
Sine squared.
I was using identity to convert those to cosines. Because once I have these, sorry, I want those as cosines because then I have du sitting over there if I let you do the cosine. So for example, I know that the sine squared is equal to 1 minus cosine squared. What do I really want though? Sine to the 4th? So that means if I just square both sides of this, I now have sine to the 4th. Which means I have to FOIL that out, right? Multiply by itself. So here's what I think I would get next. I would get the integral of 1 minus 2 cosine squared of x plus cosine to the 4th of x. And remember, I pulled out the sine of x. now we just let u be cosine, and things clean up pretty nice. So if I let u equal cosine of x, then du is sitting right there. So in terms of the u substitution, this becomes 1 minus 2u squared plus u to the 4th du. No problem with that.
That's a negative sign. Then do you negative sign?
Oh gosh, yep. So we need a negative. So I'm missing that. So thank you very much. So that should be a negative du. So we want a negative out front. And so we're out of time for fun with math today. Hopefully this helped get the idea. So mainly it's trying to pick the right trig identity. Pythagorean identity is going to be a popular one, and the half angle formula, which is a power reducing formula in this context. All right, message me if you have any trouble with the homework. I'll get back to you. And we will try trig substitution next week, which is section 3.
This isn't trig substitution.
This is not trig substitution. Trig substitution is a whole different idea. This is just playing with trig identities to variables.
And then after you find the integral of that, you have to multiply sine, the integral of sine to it, right?
So then I bring this back to the original problem, and in the original problem, oops, wrong button. I just plug that in for the answer to that part right there. We had to break that out because we couldn't do it easily. So what's going to happen is antiderivative for the sine is the negative, let's see, yeah, negative cosine. That's from this right here. And then we're going to have minus whatever we calculated on the previous page.
Okay.
And then we're going to evaluate that from 0 to pi, or pi over 2, excuse me.
So the code has got graded, but was the computer ultimately?
No, I'm still grading.
Okay, so like this.
Yeah, so the grade that you got there is going to go up.
Oh, okay,
after
so it can't
review
go
your
down.
work. The only way it could go down is if you showed me no work, then I can't give you credit. So as long as you showed work for everything, your grade will go up.
And will this third final test be the hardest test we take in class, or is that the last test?
What's it? What will be the hardest test?
Yeah.
That's the final exam, usually the hardest test.
Well, we covered
Covers
everything.
everything,
Yeah.
but you'll have your notes page. You'll have lots of handy formulas.
Very long.
It'll be a very long notes page, yeah. I'm probably going to break it into chunks, like I'll have a trigonometry page, an integrals page, physics page.
Another take-home portion?
There'll be a take-home portion too. Yeah. Yeah, so the final